let's get started again. So we developed a rate region for this multiple access channel. One comment about the way we derived these regions. We've been doing everything with typical sequence decoders. I mentioned yesterday that no one has ever built a typical sequence decoder. So you could do everything we're doing here with maximum likelihood decoding too, and use, for example, Gallagher's tools to get error exponents. It just takes a little bit more work that way, but you could do it, and once you know the mechanics, you just repeat similar steps over again. So the main reason for using typical sequence decoders again is to it's the simplest way of proving things and moving forward quickly, right? So that's one thing. If you look at this, what we have now, we actually have a more general picture than what we were really interested in. Like I mentioned, we weren't really interested in this. But now let's use that to our advantage, okay? Suppose we have the opposite situation. There's only a common message. So let's start with that, just like we did for the broadcast channel. Well, what do we have now? Well, this is just having almost like two antennas, if you like. So if these were real numbers, it's like having two antennas, and we're controlling both of them, so it's just a point-to-point channel with two inputs and one output, right? So we know what the capacity of that is. It's the maximum of the mutual information over all joint distributions of x1 and x2, right? So if this is the capacitor region, we better get the same answer coming out of this. So let's try that. Let's look at the case R1 just as a first starter. R1 equals R2 equals 0. And hopefully we'll just get the 2-to-1 antenna or 2-to-1 kind of capacitor region. Well, if we look at this region, if R1 is 0, we can, this bound is satisfied, these bounds are satisfied, this bound is satisfied, this bound is satisfied. And so I'll just get this bound on R0. Aha, it has the right form, right? So I'll just get R is equal to, let me put in both, because you'll see here I have this Markov chain still, which is the one thing that might seem unusual. So it's just the set of rates, R0, such that 0 is less than or equal to R0, less than or equal to Ix1, X2y, right? That's the region, and the capacitor region I'm claiming is the union of these sets, right? So we have a bunch, it's just a one-dimensional set, right? Starting from 0 going up to R0, and everything in here up to this number, I, x1, x2y, right? And everything here is included. And now when I take this union, I just make that set as big as possible, right? Which means is the same thing as maximizing the mutual information, right? So I'm just looking for the maximum of this, but I'm only allowed to choose PU, PX1 given U, PX2 given U. So which U would you choose to make them jointly typical in any way you want? We'll just choose U to be x1, x2, for example. We could do that here, right? Because, or we could, here we can actually do this. Although, well, yes, because from the Markov chain perspective, this is permissible here, because we could just have U being the full function controlling the joint dependence between the two. Okay, so that's, I guess, probably a little bit subtle. I mean, the main question is can we now, with this, generate any joint distribution on px1, x2, because we want to choose here the max over all px1, x2. Right? Now, well, maybe we have to be careful with that. Can we choose u to be equal to x1, x2? The answer is, well, yes, we do get the Markov chain, right? That's no problem. So in fact, we can always choose this, right? We can actually always choose this, which is kind of interesting to think about later, what that will mean, right? Because then we definitely get the Markov chain x1, x1, x2, x2. That's definitely true, is Markov. Okay, so we recover through this the thing. Let me think about this. Suppose we now put this in. We can always choose this, we said, right? But if we plug it in here as u, what's the mutual information between x1 and y given x2, x1, and x2? 0, right? So we shouldn't choose this for more general problems. The only case we should choose this is if we don't have u in the conditioning, and here we don't. That's why it works. Because otherwise we could have always chosen this, right? Okay, and the reason it doesn't work is because if we put that in here, we'd force both receivers to decode everything effectively. But anyway, well, let's just leave it at that. But anyway, it gives us the right answer, right? It's just the multi-antenna rate region. Here it is. So that's at least consistent. So that was just a quick warm-up. Let's now go to the case we're actually interested in, I'd like to focus on, and that's the case R naught equals 0. Right, so we'll do just like for the broadcast channel. Now we'll study R naught equals 0. Well, we've already seen this. If R naught is 0, let me start erasing things here. Then we're looking at this region. Get rid of this. And we said we'll get rid of this, right? R naught is 0. And like I mentioned, like this thing here is the same as having u here. So this number here is bigger than that. So this bound is redundant, so I can remove it. Okay, and so that's the region that we're interested in now. And this is a region you might be familiar with. You probably have seen it like this without the u. So let's talk about that. And that's also the traditional way of writing it. Oh, I should say something about the auxiliary variable. If R naught is 0, we can choose this u just to be 2, which is interesting, right? So u just has to be 0 or 1 sequence. Either 0 or 1. 0 will represent one mode of operation, 1 will represent another. For example, 0 might represent only that person transmitting or that. You'd think maybe u should be 3 because sometimes only that one should transmit, sometimes only that, maybe sometimes both. But here it turns out 2 is enough. You can prove that. For the more general case, it has to be bigger. So I didn't mention that, but let's not worry about that right now. Okay. Now, traditionally, an alternative, so that's one capacity expression is this. An alternative expression that you'll find in almost all books and papers, alternative, is the following. Let's look at the region px, region px1, px2. So x1 and x2 are now statistically independent. And we look at the region of rate pairs R1 and R2 that satisfy the following 3 bounds. This is the one you usually see, right? Usually you see this region presented. And then now one is tempted to just take the union over this, over all joint independent x1 and x2, right? But if you do that, you won't get the capacity region. Okay, that's the important insight. So why is that? Oh, by the way, R naught equals 0 means we only have one sequence, right? Only one sequence. And then this can even be a binary sequence. That's what we're saying. So let's plot these regions here, and let's consider, so let's, is Cmac, so this would be the natural question. I'll put a question mark here. Is this just the union of px1, px2 of R? Of course, you'll guess that because I'm putting a question mark, the answer is no, and it's not in general. Because if we plot this region, it has the following form, right? R1, R2, we get a pentagon, right? So for every case, we'll get one bound here, I, x1y given x2u. Here we'll get I of x2y given x1u. Oh, is it a pentagon? Is it a pentagon? That's already the first question. Well, for it to be a pentagon, the sum of these two must be bigger than that, right? Otherwise, like what I'm saying is there's something cutting actually, right? If this bound here was above this point, then we would get a rectangle, right? But let's see, suppose we take the sum of these two. So we can we'll show that the region is submodular through this. So submodularity means all bounds are active somewhere, right? So let's just add these two up and see if it's bigger than the last, or maybe I'll just take the second one and show it smaller, right? So let's start with this. Well, using chain rule, I have I of x1, y given you, plus I of x2, y given x1, u. So that's one of the terms. So now I have to work with this one. But here I can say this thing here is less than I of x1. We've already seen this expression before, right? But this is true, right? By putting in x2. Now I just use chain rule and I get I of x1, x2 given you, which is 0, plus I of x1y given x2u. So there you see, indeed, this is 0. Indeed, due to that inequality, I will never have the situation that I just get a rectangle and then this isn't active. So this region actually is submodular. This bound always cuts here, so we do get a pentagon. It might touch, right, but it will always be active at least at one point. So this point here is given by the joint minus this. So this is just ix2y given you. This point here is at I x1y given you. Okay, and then what we do is we still take the union, and once we take a union, we'll get regions that look like this, potentially. So anyway, usually what you get is a flat piece and then a curvy region, but in general, the whole region might be curvy. Right, so this will be the union. So this might be CMAC. And this white region will be R of PU, PX1 given you, PX2. Okay. So that's the general shape. Now, let's study this. This one has no U in it. So it turns out that if you look at this region here, we'll again get a pentagon, maybe even something similar like this. But it turns out if you take the union of these guys, you generally get a non-convex region. Okay. In general, you get a region that has the following shape. If I take the full union, I might get something like this. And then, well, let me I guess I should draw it in an overstated fashion. I will get a region that might look like this. Oops, let me make it symmetric. Symmetric. So this might be this union here. PX1, PX2, R, PX1. I guess I should call it an R tilde or something. Okay, so the problem is if you just do it without the time sharing, you in general get a non-convex region, and we know that we can do better than that, right? We know we can just take this point and operate there part of the time, take this point and operate there part of the time, and time share between the two, right? We'll do better. So in fact, this turns out to be not true, but what does turn out to be true is if we take the convex hull of this afterwards, it is the capacitor region. So that's just the important additional statement that CMAC is this region, but only once we take the convex hull of this region, where COS is the convex hull of a set S. So convex hull is just, it's just taking a sheet of paper and wrapping it around tight, right? Or if you think about it, we're just taking all points and taking all points on the line between those 2 points of the set. So the convex hull is just this. Now we wouldn't need this convex hull operation if we had kept the U inside. Now most textbooks present this as the region. The only thing is you have to then do 2 steps, the union and convex hull. I kind of like this one for a couple of reasons. First of all, we've often seen this time-sharing random variable appear in the converse naturally, right? And in fact, it takes some work still to show that these two are the same. It takes a bit of work. you have to start worrying about what the definition of a convex hull is. You have to start, working with some geometry. I prefer not to. I prefer just to write this, because proving the converse for this will be really easy. Proving it for this isn't so easy, because you have to show that this is the same as this. So why not just work with this in the first place? And there's even more important reasons why I like this rather than convex hulls, is because this sometimes misleads you to make mistakes. So there are problems, for example, we'll see for the interference channel, problems where we have two multiple access channels at the same time. So think of this as suppose we have a compound problem, right? Suppose we have two transmitters, and there's two possible MACs because we don't know ahead of time which one occurred. Then if you just do this independent stuff, take convex hull, you'll actually get a region that's smaller than the one when you're doing the time sharing inside, because doing it inside here is better than doing it outside. Here we're taking a union and then doing the sharing. Here we're doing the sharing first and then the union, and that turns out to be better in general. So there are problems. So that's why I caution to use this expression, even though that's the one that's in almost all books and papers. It's a little bit for historical reasons. So the paper, actually Alsveda, I think, even does it this way. In his original, they had a set of papers. The papers by Sleppy and Wolf tend to follow this approach. And if you look in their appendices of some of their papers, they're quite long, showing that this is basically the capacity. It takes a lot of extra work. Whereas this one is much cleaner, I think, and also, to me, gives you more insight. So that's why I like to present both, and that's also why I like to include this common message when I first present the problem. That's the whole reason I like to present it this way. Okay, is that clear? That was the main point of that. Okay, so maybe we can do maybe we can do the converse, because that's a little bit boring. And then we'll go to Gaussian channels, and we'll stick a little bit to Gaussian channels. The converse is boring, but it's also not hard. Maybe that's why it's boring. Things that are too easy are boring, right? No? Not always. Quick converse. Converse is actually not hard. And you'll see the time-sharing random variable appear. So let's just do it for the first. Actually, let's do the converse just for this region here. That way we'll just have to worry about the R1. So NR1, well, for reliable communication. And I always add that little phrase so that I don't have to worry about the Fano inequality epsilons. The rate has to be less than yn, right? That's just the usual. It's the n-to-n mut. I should write W1 and W1 hat, so maybe write that. So formally, this is true using Fano's inequality, and then that word means the error probably goes to 0, and of course by data processing this is less than yn, right? That has to be true, and now we just do the usual stuff. So except that I want to get the u in the conditioning, and I want to get an x2 in the conditioning. So what I do here is the following. This is less than if I include the other two messages here. So I'm giving the receiver both other messages, but these two are independent. So using chain rule, I get mutual information between this and this, which is 0, plus the mutual information between this. Here I can write this now using chain rule. Let me write it using, let me just write it like that. All right. Here I will now use the usual steps. So there's nothing funny here. This is actually quite a straightforward converse. Maybe one extra step. No, I can't. So, why do I have W naught? I apologize. I didn't need the W naught, right? Because I said I could keep it. Actually, maybe we should. Maybe we do it with the W naught after all. I want to do it with the W naught. That's why. Let's just do it with the W naught. I want to do with W naught. So it's going to be a small reason for it. Actually, I could do it without the W naught. Doesn't matter. Let's do it with the W naught. Then I'm doing it for the general case. Fine. Where are we? Y1I minus 1? Okay. Well, okay, yeah. I guess I could have done this a little bit. Anyway, this is just
The summation of W1 is YI or Y1?
YI, of course. Sorry, there is no Y1. I'm already still thinking of broadcast channel, right? So it's just YI for it. Thank you. Now, given W naught and W2, I can X2 is a function of that, right? So I should have done that here. I can include in here X2I, which of course is just a function of W naught and W2. So I can include that in the conditioning, right? So I may as well have X2I here and X2I here. Okay. Now this thing here, W naught W1 also gives me X1I. And so I have H of Yi given X1I, X2I, and stuff from the past. Anyway, this thing, just by Markovity, it just becomes H of Y1I given X1I, X2I, right? But I may as well just keep this W naught, which I will do. So let me keep the W naught. Do this one here, I can say is less than or equal to H1I given X2I and W naught. Okay, so this whole thing here is less than or equal to the mutual information between X1I, Y1I, X2I, W naught. So you see we have this now in the form that I wanted. X1Y given X2U. And my U is not quite going to be W naught. You'll see in a moment why, because now I can do this time sharing trick. This is the same as n, so I can multiply by n and divide by n. So we see this is an average, so I'll introduce my time sharing random variable. This is the same as I x1t, yt, given x2t, w naught t. And this is what I'm going to call my u. You see? So now if w naught was not there, it would just be the time sharing variable, u. If w naught is there, it's both. Okay? That's the main difference you have here. So anyway, now we get this expression we want. The only thing we have to check now is whether w naught t is a Markov chain for x1i and x2i for all I. And it's easy to check that's indeed the case, right? Because once I have w naught, then the two are independent anyway, right? So we definitely have this Markov chain. So this u that I've chosen even has the right form on x2t and x1t. Right, so we have the right form. Now you can repeat this now for the second bound, you can repeat it for the third bound, and also for the fourth bound if we had kept it. But the important thing for me to point out to you is what u was. U is w naught and t. And if w naught's there, it's just the time sharing variable. And that's the converse, right? Because now we have, for any coding scheme I use, the rates are upper bounded by these three, and then I can optimize over the coding scheme still. Right, and that's what gives me this union with that Markov chain appearing. Okay? There was nothing new really in the converse, just to show you that's how the converse here works. So this is nice. This problem we can solve completely, just like Shannon's point-to-point channel. This generalizes Shannon's theory for two transmitter, one receiver systems. It's a generalization of Shannon's point-to-point problem, which Shannon knew this result already. At least that's what he writes in his 1961 paper. Questions? No. If not, then let's do some Gaussian examples. So let's go to examples. Those are a little more fun usually to do. So we start with, actually let's start with a simple example even than Gaussian. Let's start with the binary adder channel, which is a noise-free channel, which got a lot of attention. I can say a little bit about some history about this channel. It's a toy example, but it helps to teach you a lot about these problems. So let's start with the following. It's something called the binary adder channel. So here the sets x1 and x2, the alphabets of the inputs and are both binary, and the channel is y is x1 plus x2, where this is integer addition. This is integer addition, so the output set y takes on values on 0, 1, and 2. Right? So it's x1 plus x2. Now let's just compute these things, and then we'll try to take the union of it too. So let's just give it a try. Well, we have to choose pu, px1 giving you, px2 giving you, but let's just do it without a u for a moment. So let's just suppose u is a constant. Then we'll just have independent x1 and x2. What's the natural choice? Well, probably uniform, so try the following. Try x1 is Bernoulli 1/2. x2 is Bernoulli 1/2. And u1 is just a constant, 0. We know we can choose it to be at most binary, but we'll just fix it for the moment. So let's just compute this. So that means we have the bounds r1 less than or equal to I of x1 y given x2. But that's just the entropy of y given x2. Y is, though, just x1 plus x2. Minus the entropy of y given x1, x2, but that's 0, right? Because y is determined by both. So this is just h of x1 given x2, but they're independent. So this is just h of x1, which is equal to 1. Right? And of course, that's the maximum it can be, right? Because x1 is binary, so the mutual information is also always upper bounded by the entropy of the minimum 1. So R2 is similar by symmetry. R1 plus R2 is a little bit more interesting because this is less than or equal to I x1 x2 y, which equals to h of y minus 0. So what's the entropy of y now if both are Bernoulli 1/2? Well, we get 3 random variables, right? Y, the probability of y being 0. So this is just going to be the summation from y equals 0 to 2 of minus p log p. All right. The probability of 0 is, if both are 0, that's a half times half is a quarter. 2 is a quarter, and then we get a half. So this number here is just going to be 2 times minus 1/4 log 2 of a quarter, if we're measuring in bits, minus 1/2 log 2 of a half, right? Right, that's the entropy. So twice, that's y equals 0, y equals 2, and y equals 1. 1 has probability half. So here we're going to get minus a quarter. That's 2, so we get 1/2. 2 times half, so we'll get 1/2. Sorry, this is what I want. There we go. Wrong bracket. Here we'll get 1 plus a half, so we'll get 3 halves. So if I plot that region now for this distribution, I get R1, R2, 1, 1, and this will be at 3 halves, right? So 1/2, 1/2, and this is here like this. Okay, that's the achievable region. Now the question becomes, can I do better than this? Now, of course, I won't be able to improve these guys, but maybe I can slow down the rate here and slow down the rate here and push something further out to get a nice curvy region here. Okay, and the answer turns out to be you can't. Now that's not obvious, right? It's not obvious you can't, but it turns out that any other choice I make here, the maximum entropy you'll ever be able to get with independent x1 and x2s is this. So this is the region. This is even the union of these regions, and since the region is convex, taking the convex hull gives us the same region. Okay. Now, but of course, if we're testing versus the u's, we'd have to think about it a little bit more to prove whether or not, you know, this is what we want or not, right? But in any case, this does turn out to be capacity. But you see already for this problem, we have some extra work to do to verify that really, you know, we can't get a larger entropy at the output than 3 halves. So the key here, if we can prove h of y is always less than a half, then h of y given u is less than h of y, and for sure we're done, right? So what we have to prove is that if we have any two independent binary random variables, the maximum entropy of y is 3 halves. That's the key here, right? And so that's what we'd have to try to work through, which I'm not going to do. But anyway, this does turn out to be the capacitor region of this channel. Now let's think about it a little bit. Corner points are always interesting, as mentioned. So let's look at this corner point here again. What is happening here? Well, user 2 is transmitting just an uncoded bit stream, right? Zeros and ones. So what's the channel that the receiver sees from user 1? Let's take a look at what that channel is. So channel, so for this corner point, channel from x1 to y, what does that look like? Well, we're just going to send either 0 or 1 for x1, and then we get 3 possible outputs, 0, 1, 2. Well, since this is Bernoulli 1/2, this guy's just sending uncoded bits, right, at rate 1. So we'll have a channel that looks like this. It stays at 0 with probably, if we send a 0, we'll either stay at 0 with probably half or go to 1 with probably half. If we send a 1, we go to 1 with probably half, or to 2 with probably half. Have you seen that channel before? That's an erasure channel, right? What's the capacity of an erasure channel? 1 minus the erasure probability, which is 1 minus a half, is a half. So that tells you how we can achieve that point. Right? So user 1 has to build a good erasure correcting code. So again, even though there's no noise here, because of the interference, the problem gets interesting. User 1 actually has to use a sophisticated code. LDPC code, Raptor code, you know, Reed-Solomon style if you have large alphabets, but okay, here we don't. Here we have binary alphabets, so we have to stick to binary erasure channel correcting codes to get close to that point. So that's interesting. Now, an erasure correcting code is never has 0 error, right? So one interesting question you could ask for this channel is the following. This is something that was a popular topic in the end 70s and early 80s, is what is the 0 error capacity of this channel? So 0 error capacity means we can really communicate 2 messages without any errors whatsoever. So for example, I can operate here at 0 error, obviously, because I just send, you know, user 1 just sends 0, and then there's no error. User 2 just sends 0, and certainly I can timeshare the 2, so certainly the 0 error capacity is bigger than that. But is the 0 error capacity here the same as the epsilon error capacity for this channel? Interesting question, not so obvious. This point here, the way we achieve it with erasure channel coding is not 0 error, but maybe we can get as close as we want with 0 error. Okay, so this was a popular topic. You find papers on uniquely decodable coding, some words like this, that's source coding language. But anyway, people were designing combinatorial structures to find out what the best possible 0 error capacity is, and they were never getting close to here. They're always around 1.3 some rate rather than 1.5. And so there was a paper, so Rüdiger Urbanke, when he was at Bell Labs, published a paper showing that you're bounded away from this corner point if you're interested in 0 error. So he showed that the 0 error capacity is not the same as the epsilon error capacity. So this was still during his early pre-LDPC coding days. He was also working on problems like this. So it's kind of interesting. So anyway, already a simple problem like this can be very fascinating due to the, you know, distributed coding that you're doing. Okay, any questions about this. So let's now go to the more interesting, the class of channels we want to discuss in more detail. Those are the Gaussian channels. The Gaussian channels are very rich for this problem. Very nice because we have a capacity result. And we want to look at ways of getting to capacity, and it's also really interesting because it's very practical, right? I mean, many mobile stations transmit with only one antenna, right? And so scalar Gaussian problem is really interesting. Perhaps we will allow multiple antennas at the receiver, but the most interesting case for many problems of today of practice, I mean, the future mobile radios might really transmit over both. And you know, so your laptops might even be able to do that already. Some of the newer ones, I don't know. But for most mobile terminals, you have one scalar streams and either scalar or vector receiver. So those are the most popular models studied right now. Okay, so let's go to Gaussian channels, and we'll start with a scalar output channel. So scalar input, scalar output. So now we're already getting closer to applications. For the broadcast channel, the more practical applications are the ones where you had a multiple antenna transmitter, so it's a little more difficult to deal with at the beginning. But here we're okay in some sense, but we can talk about that. Okay, so let's do the additive white Gaussian, so scalar, additive white Gaussian noise channel. Okay, the usual model, Y, and for now let's just make it a channel without, you know, I should be adding gains here, like gain H1 for one user, H2 for another user, but I can always swallow the gain into the power constraint, right, if I want to. So let's just work with this, plus Z, where Z is zero mean, variance. Do I want to stick with 1? I think I stick with 1. No, well, here I have n. Well, let's do n for now. Can later make it 1 if we want. P1, then we have the power constraints, 1 over n, summation I equals 1 to n of the expected value of x ki squared, less than or equal to p for k for both users, 1 and 2. So we have power constraint k, so P1 and P2. That's my problem. Of course, I should have now derived the achievable region with power constraints, you know, but the only thing that changes there is that the union is a constrained union. It's the union over all joint distributions for which, you know, the expected cost constraints are met. So usually these cost constraints don't add anything deep, so we'll just work with it. Formally, I should prove that, I suppose, but anyway. Okay, so how would we code for a problem like this? Well, we'll start with the same idea we had before. Let's start with u as a constant again. Or maybe we can work right away with, let's not. Let's keep u general. In fact, we'll just work with the expression and see what happens. So let's look at this problem. Let's start with this one, because here we can actually show that Gaussians are optimal. Let's start with this, okay? So the first thing to realize is u is here everywhere in the conditioning, so it's just going to be an average. I should even maybe take an integral because I could permit u to be continuous. Why? Remember what my bound, well, I could, here u equals 2 is enough actually for this problem. But if I had all rates, then u equal 2 may not be enough, and the alphabet of u will depend on the alphabet sizes of the objects, and then it could even become an integral. But anyway, here we know u equals 2 is enough, so, but let me just work with this, this sum. Right, this is just by definition, right? So that's just an average. Now, let's write this out. H of entropy, differential entropy of x2, u equals u, minus h of y given x1, x2. u equals u, right? Now y is x1 plus x2 plus z. So this thing here is h of x1 plus x2 plus z, but since I have x2, I can subtract it out. So I'll get x1 plus z, given x2 and u, but given u, x2 is independent of x1 and z, so this is just given u equals u. Minus, and here I just get x1 plus x plus z, but I can try to get z. Z is independent of everything else, so I just get 1/2 log of 2 pi e times n, right? Because that's just a Gaussian variable, right? So this is all with equality, no bounds yet. And now, what's the variance of this? Well, the variance of this is upper bounded by p1 plus n, right? So an upper bound on the differential entropy is going to be the Gaussian version. This thing here is less than or equal to 1/2 log 2 pi e p1 plus n. And that lets me say this whole thing is less than 1/2 log of 1 plus p1 by n, right? Because, I mean, I can remove it out of the sum. I just get something independent of u, and then I just sum over the u, right? So that's nice. So I have this upper bound immediately. Similarly, I'll get these upper bounds here. And can I achieve them? Well, yes. Just set u to be a constant, and I get equality here if and only if x1 is a Gaussian random variable with 0 mean of power p1. And so just choose it that way. So in this case, it's quite easy to see what even what the optimal pu, px1, px2 giving you as a pu can be just a constant, px1 can be Gaussian, px2 can be Gaussian. So the whole region just collapses into the following form. So the capacity region here turns out to be the set of rate pairs without a union anymore, because the union is already there. It's R1 less than or equal to 1/2 log 1 plus S and R. 0 less than R2 less than or equal to 1/2 log of 1 plus P2 plus N. And the last one will be the I, x1, x2, y, so we'll get the entropy of y, the entropy of y, the variance of y is at most p1 plus p2 plus n, so we'll just get r1 plus r2, same bounding techniques. Right, that is the capacity region of this channel. So now let's plot this. That's nice. So the Gaussian cases are always nice because they often simplify a lot, and because you know that uncorrelated means independent, so using MMSE stuff is always the best thing to do because you get orthogonality principles. So always for Gaussian, you're always using the same tools, right? MMSE estimation. So let's plot R1, R2. Here we get 1/2 log 1 plus P2 by N. Of course, that's the best rate we can get, right? Because that's the capacity. If you just have a point-to-point channel, here we get 1/2 log of 1 plus P1 plus N over N. Of course, that's the best rate. And then this goes out, and here we get this bound here, and these bounds here, let's take a look at what this rate is. Well, it's just this minus the first one. So let's see, what is that? And let me do it this way, I'll put the n up. So I get p1 plus p2 plus n by n minus this, which is just 1 plus p1 by n, so we get n over p1 plus n. Those cancel, and look at what we get. 1 plus the signal to interference plus noise ratio. So that's very nice. We're always working with signal to interference plus noise ratios, and that suggests, of course, something quite important. Namely, it suggests certain receiver architectures, which are very important in practice and weren't so obvious, and are all the rave now with NOMA again, non-orthogonal multiple access. You use successive interference cancellation, so we'll talk about that in just a second. Of course, these methods are as old as multiple access channel theory from the 70s, so there's nothing really new conceptually there. Again, tailored to the newer channel models, perhaps. Okay. Right. So that is the MAC. So this, of course, suggests a certain way of communication that I've already mentioned. So let's talk about these methods. So this suggests, if we go to the corner points again, we're often interested in corner points. Let's look at that corner point. That means that user 2 is just transmitting. Let me now erase this since we have here 1 bit. So here we just have time. Common timing, that's the common information between the two. This suggests doing the following. User 2 will just map its messages onto a really good LDPC code, or followed by 16 QAM modulation, which is shaped to look like a Gaussian, right? So you're trying to operate close to this curve. Oh, actually, maybe we can, before we go so far, let's play around with this just a little bit. Let's go to high SNR and low SNR, right? That's always interesting, right? So before I go to the decoding, what happens here if the P's get really big or the N gets really small? What's going to happen? What's going to happen? So what happens here? Well, if N gets really small, the 1 won't be important. And well, if N gets really small, here we'll get P1 over P2, right? But this will blow up, right? Maybe I can view it differently. Suppose I make P really big, right? If P is really big, these numbers will get stuck at approximately 1, right? This will get stuck. And so will this, but this will start blowing out more and more, right? So if I drew this, I'm going out here, and I'm going way out here, but these numbers are stuck where they are approximately. So, and you'll see I'm getting more and more of a sort of a shape that looks like just a diagonal line. Huh. So at high SNR, I'm just almost getting a diagonal. But if I get a diagonal, it's getting close to time sharing, right? Because time sharing would be the simplest version of time sharing, and we'll talk about more sophisticated version in just a second, is just to operate there, right? So, but the bigger SNR looks like we're getting more and more just to get diagonal line as a picture. What happens at low SNR? Well, perhaps the opposite happens. So at low SNR, the P's are getting really small. The P's are getting really small, so log of 1 plus something, when that number is small, is approximately that number, maybe scaled, depending on what base I take the logarithm. But I'll get P1 over N, P2 over N, and P1 plus over N plus P2 over N. In fact, at small SNR, what's going to happen is the opposite kind of effect, is we'll effectively get a bound that looks like this. It's almost a rectangle. And so actually at low SNR, we can communicate as if there was no interference. Okay, and it turns out that is actually true, and the best way to communicate is actually a method we're about to discuss, namely time sharing with properly set powers, with power control. Okay, so we'll talk about that in just a second. So at low SNR, the capacity region looks almost rectangular. That's the important thing. So high SNR, Cmac looks diagonal, looks triangular. Low SNR, Cmac becomes or looks rectangular. Okay, and actually that second, both points are important, but the second important is especially, this last point is important especially for certain practical systems where you operate at low SNR. Where do you operate at low SNR? Well, for example, ultra-wideband communications. If you're sending with ultra-wideband communications, you have a lot of noise in your system because you're using a lot of bandwidth, right? So at ultra-wideband, we can communicate as if there is no interference. Okay, we'll talk about what that means in terms of strategies in just a second. So now, anyway, after all that, I just wanted to mention that first because it's kind of interesting to think about. Let's talk about successive interference cancellation. So going back to the corner points without talking about how the stuff behaves at different values of p's and n's, let's go back to the corner point. Okay. This suggests then user 2 just transmits, and user 1 transmits at a lower rate, and his SNR is this, so it really suggests the receiver should first decode this user by treating the transmission of the other user as noise. Now, the sequence of the other user is not noise, right? It's actually a sequence from a code book. It's actually not IID. However, we're going to treat it as if it was IID, so we're using a mismatch decoder that treats the interference as if it was noise, and you can show that you can then still decode at this rate. Okay, but that would take a little bit of extra work to deal with mismatch decoding to show stuff like that. But anyway, we'll do this. Okay, so the idea is, so this is called sometimes the whole thing is sometimes called multi-user detection, MUD. This is called successive interference cancellation, successive interference cancellation, or SIC. Sometimes you see that acronym. And the architecture goes as follows. We get Yn. The receiver sees Yn, so these are the samples at the A to D, out of the A to D converter. We'll build a decoder for user 1 that is mismatched. It treats, treat interference, this is mismatched in a way that it treats the interference as noise. And out of that, we'll get an estimate for W1. And the rate at which I can decode turns out to be just 1/2 log of 1 plus the signal to interference plus noise ratio, which is natural to expect. Then we have to re-encode encoder 1, right? We have to re-encode. We get X1N. Then we subtract that from this. And then we get a signal that if we decoded this correctly, if W1 hat is the same as W1, well then we'll just have a clean channel and can decode at the decoder 2. W2 hat, right? So that's the architecture. So this kind of architecture, I know, just talking with some engineers, I know Qualcomm implemented this stuff already in the early 2000s in some of their chips. I don't know if it was in certain products or not, so I don't know more details, but it's something that was done. There is something, there's a few important details to think about here. Getting back to our synchronization, usually if you have two mobile stations, they may not be perfectly synchronized, right, up to the symbol level, right? They might be offset by half a symbol or so on. So what you have to do then is you first have to get the timing right for user 1, right? So you have to do a resampling or interpolation to get the right samples for user 1. After you do your decoding and re-encoding, we have to add another box here. We'd have to add another box, so you need two boxes basically here, timing user 1, and then we need another box here that again interpolates so that we get the timing for user 2, right? What I mean by these boxes is just, a sync interpolation for band-limited functions, right? So you have to make sure to build stuff like that in if you're taking into account the actual waveforms that you're considering. So there are some extra details to worry about when you map the real system, of course, onto the model. But it can be done, right? It's not something that's so hard to do. It's just something to keep in mind. Okay? And through that, you can get close to that corner point. Okay. Similarly, we can communicate on this corner point by using another mode of operation where this guy sends at a lower rate and this guy sends at a higher rate, and then we can time share between the two. And so there you see this, you know, binary time sharing going on to get to any point. In particular, often you're interested, you know, in this point right here in the middle. Or anyway, you want to be on this face, but sometimes you want to operate at different areas depending on what the you know, service package that your user has, quality of service that your user has bought. You know, you might want to operate at one point or the other. Okay, so any questions? Yes.
Apart from the corner points, the other points we are now achieving by time sharing. Are there any possible methods we can do without time sharing?
Yeah, so that was going to be one of the next topics. I don't know if I have time to talk about it before lunch now, but I will talk about it after lunch, yes. So we'll talk about 3 different methods to avoid time sharing. So one disadvantage of time sharing, like suppose I want to get to here, is that I have to now use 2 modes of operation, right? And that increases the delay and the control overhead. So it's natural, if I want to get this point, I'd like to do it within one block. How do I do that? Okay, and we'll talk about 3 different methods to do that after lunch. But before we go to lunch, let me talk about time division, right? So we talked already about time division often before. One way of doing time division is, well, user 1 gets the channel for this fraction of time, user 2 gets the fraction for this type of time, and you share, right? But of course, if we do that, then user 1 is only sending at a lower power, at his maximal power for, say, half the time, but actually is not using any power for the other half. So actually we could boost that user's power by a factor of 2 during that time, if we have a block power constraint. Of course, if we have a symbol power constraint, then this is the best you can do. But suppose we now have a block power constraint, and let's compute what the rates are for TDM or FDM if we do a smart TDM and FDM with power control or power options. So we can do this method either in the frequency domain or time domain. The advantage in the frequency domain, of course, is then you don't have to synchronize the users in time, but you have to synchronize them in frequency. The advantage of doing TDM is you don't have to synchronize them as much in frequency, but you have to synchronize them in time. But either way works the same. So what do we do? The strategy is user 1, so often the encoders are called users. User 1 sends at power P1 over tau, a fraction of tau of the time. And if we want to generalize it, user k, you know, well, okay, so we have 2 users, so if we had more, we could just have it more general notation. But anyway, user 2 sends at power P2 by tau bar. Tau bar is 1 over 1 minus t tau, a fraction of tau bar of time. Right, and so now we just have to compute what the rates are for this strategy. So what are the rates of this strategy? Well, R1 is going to be tau 1/2 log of 1 plus P1 by tau n, and R2 is equal to tau bar 1/2 log of 1 plus P2 tau bar n. For example, if we choose tau to be 1, then tau bar is 0, this is 0, and we're operating at this point. Otherwise, we're up at this point, but let's see what happens in between. And we'll choose one particular tau. Suppose I choose tau to be P1 over P1 plus P2, just as an example. Okay, so for example, this would be 1/2 if the powers were identical. What's going to happen? R1 is equal to P1 over P1 plus P2 times 1/2 log. Well, P1's cancel and we get the sum rate on top bound. And since 1 minus tau is P2 over P1 plus P2, we get the same thing. And the remarkable thing about this choice then, if we sum up these two rates, what do we get? If we add these two rates, of course this sums to 1, we just hit the sum rate bound. So what that tells you is that this TDM method gets rates that go like this. It actually touches this boundary, comes down. So in fact, TDM FDM is optimal at one point, and in fact it always touches at one point. This is TDM FDM. And here we even get it touching. FDM is even optimal. So this kind of plot was presented, I think it was by Viterbi in a paper in the 90s, and it was used as an argument to say, well, why do we need multi-user detection? I mean, look how close we're getting to the whole region if you look at this picture, right? And yeah, if you look at this picture, you say, well, what's the point? I mean, why not just use orthogonal transmission? You know, you could be disappointed by this point. Sure, we're not getting right to the corner, right? But, you know, it doesn't look so far away. So with this in mind, it turns out that it's a little bit more subtle than this. Namely, here I've drawn a picture where P1 and P2 are about equal, right? Now, in many wireless situations, P1 and P2 are very different because the user who's far away will have a much lower effective power than the user who's close. So you have near-far effects. So when you have near-far effects, let me just draw you the cartoon of what happens. So let's suppose, you know, one signal could be 20 dB bigger than the other, right? 100 times or 1,000, 30 dB. Well, what would you get? Like, suppose user 2 is far away, and user 1 is really close to the base station. Then we might be here at 1/2 log of 1 plus P1 by n, and we might be, you know, here at 1/2 log of 1 plus P2 by n, right? So we might have a situation like this, and when you plot this curve, you'll get something that looks like this is the capacity region. This is really low, actually. Looks like something like this. Okay, and now, if we do this method, sure, we hit the sum rate bound, but where do we hit it? It turns out we hit it really close to down here. So if I drew what TDM FDM does, if you drew this, you would see this. Right? And now, if we use successive interference cancellation, we can still operate here. Whereas with TDM FDM, we're only, let's say we want to, suppose we back off the strong user just a little bit. Then with TDM FDM, we're only operating at half the rate, approximately. If you measure this, it'll be about half, you know. So what that says is if we're interested in fairness, like, why should if I decide to operate here, the main point here is even with TDM FDM, backing off from the strongest user a little bit in rate gives the weaker user at least a reasonable rate. Like, suppose this here is 1 megabit per second, and this here was 100 kilobits per second, right? So that's better. It's better to back off from 1 megabit per second to maybe 900 kilobits per second to at least give the weaker user 100 kilobits per second rather than nothing, right? So that way you'll make your people happier. At least, you know, you have a slow internet access, but at least you're getting something. But now doing successive interference cancellation, we can offer the user, rather than 100 kilobits per second, we can offer them 200 kilobits per second. So that's the business case in the sense of using successive interference cancellation. We have to do a lot harder work. We have to, do a decoding, subtracting, synchronization, resampling. It all takes processing power, right? And it's not so easy to do, but for a base station could probably do that, but that's what you'd have to do. And that way you improve the rates, okay? And if you have 3 transmitters or more, these kinds of effects get a little bit bigger all the time, so that there it makes sense to start using successive interference cancellation. So this picture doesn't tell the whole story, right? That's the main point. Okay, so it's important to realize, and often you see this often happening. Often when you do information theory for some simple problems, you get rates that disappoint you, but the fundamental methods are almost always important in practical cases anyway, because once you start looking at more other problems, you realize, oh, actually I am gaining something. And it may even make your company competitive as compared to another company. So these gains can be important if you're selling products, of course, or selling intellectual property, or trying to protect intellectual property, and so on. Okay, any questions about this?
Practical gains would be little less because we are ignoring, this is basically the error propagation kind of thing.
Oh yeah, this is right. So if you have a successive chain, you have error propagation, but usually error propagation increases error probabilities linearly, whereas coding decreases exponentially, right? So you just have to make sure, of course, that your error probability is at 10 to the minus 5, and now you might have 2 times 10 to the minus 5, but that's not such a big deal. But it's true, yes, there are these issues. So you have to have, the codes have to be reasonably good, but both of them, not just one of them. But more important is even the first step is more important to get good. But yeah, absolutely, yeah. Yeah. And so after lunch, I'll talk about, I promised 3 methods to get to these points without, to get to any of the boundary points, not just one. Here we found one, but I'll talk about 3 other methods. One of them is rate splitting approach to multiple access. That has also its disadvantages. We'll talk about that. One is just doing soft interference cancellation, so doing iterative processing. We did a successive interference cancellation, but actually we could feed back the soft information and do a turbo loop. And so I'll mention that briefly. And the third method is actually a neat method, which is, I don't think in any textbook up to now, but it's a nice little trick, what you do is you shift the transmissions. You take blocks and you shift them a little bit, or shift them a lot, and then you'll automatically be able to operate at different points. And I think that's the most practical method, is actually just by time shifting. Nothing special, just shift. Add some offsets to your transmissions. It's kind of a neat trick.